So today we'll start with the problem of linear quadratic regulator. So far we have discussed the problem of state feedback design for the single variable case and also for the multivariable case. We have also seen the robust uh, controller design problem also. So the main idea in the problems, whatever we have discussed, lies in having the set of desired eigenvalues. So if you recall that whether we have taken the eigenvalue assignment problem or the uh, Lyapunov design problem for the controller, we have the set of desired eigenvalues, and we also had a brief discussion on that based on the transient and steady state characteristics, you can have those information about the desired set of eigenvalues. And whenever we specify those transients or the steady state performance criteria, they form the control objective basically. So now here we'll see another viewpoint of designing a state feedback controller where we now define the performance index explicitly in terms of the input output variable. So, or basically, this is also part of the optimal control design problem. And today we will see a brief overview that how the controller can be designed using that viewpoint. So the first standard problem is called the linear quadratic regular problem. The this linear term basically comes from the fact that we are designing a system or we are designing a controller for a linear system, which is we have been discussing from the beginning. That is a continuous time linear time invariant system. Quadratic word comes basically from the fact that whatever the performance index we will formulate or we want to optimize, it is quadratic in nature. We will pay more focus to to this aspect as we go along the lecture. The regulator, we have seen one regulation problem. So the idea remains the same, that the state or the output should reach to zero, or the state in fact should reach to zero, which is a regulation problem. Okay. So the problem in this framework can be defined as that given a continuous time LTI system, which is given by this, the linear quadratic regulation problem or the regulator problem consists of finding the control signal u of t that makes the following criterion as small as possible. So we define the cost function which is the integral from 0 to infinity, and inside the integrand we have the quadratic functions of the output signal y and the input signal u with some weightage matrices q and r. Now these q and r matrices are the positive definite matrices. In the previous lectures we have discussed about the quadratic forms and also about the positive definite matrix. So now if I write only this integrand, the first integrand, so this integral is basically this y transpose of t and y of t. Say for example, forget about the q or take q as an identity matrix dt. So if you recall that this part by using the property of the norm, I can define this as 0 to infinity and norm of y square dt. Okay. Now let's write this integral in some another variable z. Where z could be either state or the output variable y or the input variable u. Now if it is an input variable u, in some of the tutorial problems we had seen that this define basically the energy in the control signal or the control energy. Now if it is only the output signal y, then we call it the output energy. So the basic idea here is we want to minimize the energy in the input output signal, and at the same time we want to design a controller or we want to design a state feedback controller such that this these energies are minimized. Okay, so the following terms provides a measure. First is the output energy, another is the control energy. Now this performance index, it's because of its nature, that is quadratic in nature. That's why it is called an LQR problem, which we have defined in terms of the output variable and the input variable. Now if I represent, let's say this, I choose another function j and define 0 to infinity, and I use e of t, which is a signal, and some, let's say, some weight matrix e dt, and if I define e as r of t minus y of t, where r is my reference signal and y is my output signal. Now if I want to synthesize a gain matrix k such that this performance index is minimized, so I am actually aiming to minimize this energy so that my error becomes equal to 0. Now instead, now when we see or when we incorporate the property of the norm, we know all these quadratic forms can be represented by these norms, and from the property of the norm we know that this norm is positive, or it would be 0 if and only if this z is equal to 0. Okay, so it cannot have the negative values. So the minimum value the this can go is only 0. Okay, and when it becomes 0, e becomes 0. That is to say, my output signal would track the reference signal. Okay, so most of the control problems we had discussed so far can also be formulated in this framework. So we'll see now the solution of this problem. So in LQR, taking this quadratic cost function, we seek a controller that minimizes both energies. However, decreasing the energy of the output requires a larger control signal, and a smaller control signal leads to larger outputs. So we'll pay more attention to it, and in fact we had seen in some of the tutorial problem also in the past couple of weeks that if we want to achieve faster tracking, then in that case the control energy is much higher. If we want to track the reference signal with the slow dynamics, then in that case the control energy required the control energy is small. So we can also play with those aspects by changing the value of these weight matrices, which are the positive definite matrices. So when R is chosen much larger than the Q matrix, what does it mean? That we want to penalize more control energy. We want to penalize more energy, and the most effective way to decrease JLQR, this cost function, is to employ a small control input at the expense of the large output. Meaning to say, the difference between the reference here we have the origin, the difference between the origin and the output y would be larger in that case. Okay, so there is some trade-off in selecting these matrices Q and R. If we choose R higher, meaning to say that we want to penalize the control energy more than the output energy. If we choose Q higher, then we want to penalize the output energy. Meaning to say, in that case, our control energy would be higher also, because we need faster control action to reach towards to the reference trajectory. So before solving this problem, we will introduce a couple of definitions which would help us to synthesize the feedback gain matrix K. So the first definition is about the feedback invariant. That given a continuous time LTI system, this one of where the state is having dimension n, here u is having a dimension k and y is dimension m, we say that a functional h, which is only a function of the signal x and the signal u, that involves the, or we call this functional a feedback invariant for the system CLTI whenever its value depends only on the initial condition x of 0 and not on the specific input. Okay, so this definition has some in fact this is the, that's why the name originates of this functional as feedback invariant, because it is not affected by the control trajectory, but its value depends entirely on the initial condition. Okay, so by introducing this functional h, we have another result that for a symmetric matrix P, the functional h defined as the negative of the integral from 0 to infinity of this signal transpose P into x plus x transpose times P times this signal. We call this functional, which is defined as this, is a feedback invariant for the continuous time LTI system as long as the state trajectory xt satisfies that the value of this signal becomes equal to 0 as t tends to infinity. Okay, so this functional, which we have characterized in terms of the state and the input trajectory, is called the feedback invariant under this condition. So we can see a quick proof of this one. So if you pay attention to this part, this is nothing but the x dot. Okay, so we have replaced this part by x dot. Similarly here we have replaced by x dot. Now if you recall, in one of the lectures we have discussed that I can express this overall part as the derivative of this quadratic form x transpose px. Okay, now since we have the negative sign, so I need to compute its value of this quadratic form at t is equal to 0 minus the value of this as t tends to infinity. Okay, now if you see here, we have x of 0 transpose p times x of 0 minus limit t tends to infinity x transpose px. We have these conditions given to us that the signal xt becomes 0 as t tends to infinity. So this part would go 0 and the remaining part is this one. So we see, according to the definition, that this functional becomes a feedback invariant because its value depends only on the initial condition of the state trajectory. Okay. Now suppose that we are able to express a criterion J to be minimized by an appropriate choice of the input signal U in the following form. So this criterion is important to pay attention. So we have expressed this J as equal to the feedback invariant function H plus integral of some function gamma, okay, which is a function of x and u, where H is a feedback invariant, and this function has the property that for every x or for every n-dimensional state vector, this is satisfies that the minimum value of this function over u should be equal to 0. Okay, now it is pretty much straightforward that under this scenario we can write the control signal as the argument of this thing, because we are basically computing those u for which this function becomes equal to 0. So the argument of this function would give me the control signal u of t. Okay, so we know that this u will minimize the criteria J, and the optimal value of J is equal to the feedback invariant now. Okay, because if I want to minimize this function, minimizing this part would go only 0. So from here I compute u. Now once this part becomes equal to 0, and this part is independent of the time because its value depends only on the initial value of the state trajectory. So I would get this fixed value whenever this function is minimized or whenever this control signal is applied in the feedback loop. Okay. So note that it is not possible to get a lower value for J. Since the feedback invariant H is never affected by U, so once we have computed or once we know the initial condition or the initial value of the state, its value is fixed. Okay, and as we have seen in the previous result, or generally what we have seen, that this function could only get the positive value. A smaller value for j would require the integral on the right hand side of the criterion to be negative, which is not possible since this function can at best be as low as 0. Okay. So this would be the minimum value of this criterion whenever we apply this control signal. So again, proceeding with this criterion, it turns out that the LQR criterion can be expressed as this function for an appropriate choice of feedback invariant, right? In fact, the feedback invariant which we have introduced earlier can also work provided that we choose the P matrix appropriately. So this function we have introduced in one of the results, that this functional is a feedback invariant under this condition. This condition is important for us. We will see why. Okay. So now we'll play with this function h to see the similarity between this criterion and the LQR criterion we started with. So to check that this is so, we add and subtract this feedback invariant to the LQR criterion and see. So j LQR I can write, or what we had seen, 0 to infinity. So this part is y transpose and this is y. Okay, so there should not be transpose, so this transpose won't be there because this is y. Similarly, this transpose won't be there. Plus u transpose ru. So we add this functional h and subtract this functional h. Now this h we already know is expressed by this one, or in the compact form I can write as minus 0 to infinity x dot transpose px plus x transpose px dt. Okay, so when I substitute this one, this is the same what we have written. This is x dot and again this is x dot. Okay, and since it was having a negative sign, so subtracting it would add it into the overall integral. Okay. So now we will arrange a couple of terms to visualize that what is, or to simplify the things for computing the feedback gain k. So we have coupled all the, or we have combined all the terms for which the x transpose is common in the pre-multiplication factor and x is common in the post-multiplication factor. So here we would have x transpose A transpose P times x. So if you see that onto the left hand side and the right hand side, we should have this one, x transpose x. So this part would go here. Similarly, by taking the transpose of it, we would have x transpose A transpose and P times x. So this is the first term. So this first term will become this one, and the next term is this one, which is x transpose PAX. Okay, this is the third term. Now the rest of the term we have written here. So this one become u transpose RU, and the two terms would add up because from here we would have u transpose B transpose P times x and x transpose P times B into u. Now these two terms, because they are scalars, they would add up. So we have written that twice of u transpose B transpose P times x. Okay. Now by completing the squares as follow, we group the quadratic term in u with the cross term in u times x. So now we introduce this quadratic form where you can express this as u tilde, where u tilde is u plus k times x, and this becomes u tilde transpose. Okay, and here k we have replaced by R inverse B transpose into P. So if I open this quadratic form, we would have U transpose RU plus X transpose, and by putting K into this, we get this long expression plus twice into this. Now if we see the similarity between this expression and this expression, the rest of the part, this part I can express as, which is also available here. If we see these two parts, I can express as this whole part minus of this whole part. Okay. So this is what we have written here, that JLQR is equal to the feedback invariant function H, and inside the integral, this is the term which we already had previously. Now this term we get if I replace this and this by this minus this. Okay, and since it also contains X transpose and X as pre-multiplication and post-multiplication vectors, so we have combined that term inside this term. Okay, minus of this one and the rest of the part as this one, right? So now if we pay attention to this function, that if we choose this part is equal to 0, plus if we choose this part equal to 0, the rest of the part remains J is equal to H plus integral of 0 to infinity this whole, or let's say U tilde R U dt. Okay, now if you pay attention to this form and to this form or the criterion we had introduced inside this integral, so this is nothing but equal to your gamma function. Okay, so this is nothing but your gamma function is U tilde R U. Okay, now which has a minimum equal to 0, so this would be equal to 0 if we have U is equal to minus K times X, and this is nothing but our state feedback where K is expressed as R inverse B transpose P. Here the inverse of R is possible because R is positive definite already in the definition of the cost function, and P we need to find out. Okay, so now the problem of designing the feedback gain K, the problem now boils down to compute the matrix P, and the matrix P would be computed from this equation. Okay. So when I apply this U is equal to minus K times X to the LTI system, we know already that this would become our closed loop system. Okay, with the closed loop state matrix A minus B R inverse B transpose P, where instead of finding the matrix K, we need to find the matrix P. Okay, and here you would realize that this equation is a nonlinear equation. So this we have one of the result, the optimal state feedback, that assume that there exists a symmetric matrix P to the following algebraic Riccati equation. So this equation what we have find out through this whole procedure. So this equation is basically defined as the algebraic Riccati equation, for which the closed loop state matrix is a stability matrix. So this point is a very important point. We will come on to this point a bit later. Then the feedback control law U is equal to minus K times X, where K is defined by this, stabilizes the closed loop system while minimizing the LQR criteria. Okay. So why I say that we need to find a symmetric matrix P for which this closed loop state matrix is a stability matrix, because there are many matrices P which satisfies this equation, but for some P this closed loop state matrix might not be a stable matrix or its Hurwitz. And since we want to minimize the cost function over 0 to infinity, we definitely want that the state trajectory should reach to 0 as t tends to infinity. So there might be some p, for which this closed loop state matrix is not stable matrix, but still it satisfies this matrix, this equation. Okay. So generally the problem of the optimal control design and the stability problem are two different problems. For optimality, we need to find one p which satisfies this equation. But for some p, if I compute this control law u and apply to the plant, the closed loop might not be stable. Okay, but for some p, I could still have the this matrix as a stable matrix. Okay, which ensures that my closed loop would be stable. Okay, so we can also say that the symmetric p which satisfy this one, for which this is a stability matrix, we can also call those p as stabilizing solutions. So basically we want to find all the stabilizing solutions of this equation so that this closed loop state matrix becomes a stability matrix. Note that asymptotic stability of the closed loop system is needed because we assume that this part should become equal to 0, which is equivalent to saying that the state trajectory should reach to 0 as t tends to infinity. Now here we have I have put one paper in the footnote where we have discussed another viewpoint of discussing the linear quadratic problem using Krotov sufficient conditions. So you may look at this paper to get to dwell into more into this subject. Okay. So the ARE itself already provides the clues about whether or not the closed loop system is stable. Indeed, if we write the Lyapunov equation for the closed loop, okay, so this is our let's call it A bar or ACL, A matrix of the closed loop. So this matrix becomes ACL transpose P plus P times or ACL. Okay, now if I simplify this equation, I would get A transpose P plus P times A minus twice of this whole part. Okay, which could be expressed as minus Q bar, which would always be a negative definite, this one. For Q, positive definite. Okay, in case P is a positive definite matrix and Q bar is a positive definite, we could immediately conclude that the closed loop system was stable by Lyapunov stability theorem. So here we have recalled one of the result we had discussed during the stability week, where we have established the Lyapunov stability theorem for continuous time LTI systems. In MATLAB, there is a direct function available which is defined by its own name, LQR. So here on the left hand side we give three outputs of this function whose arguments are the AB matrices. This QQ is nothing but C transpose QC, which is the weight matrix in the cost function. This RR is the weight matrix of the control energy, and NN we have not discussed about this NN, so for the moment you can put NN is equal to 0. So here NN, so let's say, we have discussed this J 0 to infinity as the norm of Y weighted by Q plus norm of U weighted by R. Okay, so there are some couple of terms, let's call it phi, which are the multiplication of Y and U or X and U. Okay, so the weight matrix of those cross terms is basically NN. Now here, since we have not discussed these cross terms, this part you can put NN is equal to 0. Okay, so once you input all these matrices, you will get three outputs. K, so K would be the optimal state feedback matrix K. The solution P is the solution of the algebraic Riccati equation, and E gives you the poles of the closed loop system. Okay. So by using this method, you can also design the multivariable the state feedback gain matrix for the multivariable system as well.